Greetings everyone and welcome back to the online lecture series of microprocessor systems. This is the fourth lecture of this series, and in this lecture we are going to discuss about the basic computer organization, instruction codes, addressing modes, and computer registers. And in this lecture we are going to start the chapter 5, the basic computer organization of the textbook by Maurice Meno. The contents of Chapter 5 include instruction codes, computer registers, computer instructions, timing and control, instruction cycle, memory reference instructions, and so on. So we'll start with what are instruction codes and what is the structure of an instruction. Every processor has its own design, including different registers, buses, microoperations, machine instructions, and different capabilities. Modern processor is a very complex device and it contains many registers, multiple ALUs and floating point units, ability to pipeline and schedule different tasks. However, as this is the basic course and it is aiming to develop the basic understanding of the students about the how the computer works, how a basic computer works, we are going to study the basic computer organization through an architecture or through a design that was around that was designed around 35 to 40 years ago by Maurice Meno. And using that architecture, we will develop the know-how of students about the basic computer organization. So let's start with what are instructions, what is a program, and what is a microoperation. A computer program is a sequence of instructions, and a computer instruction is a sequence of microoperations. And we already discussed what is a microoperation. Any individual operation that requires one clock cycle to operate. So an instruction can have multiple microoperations. For example, if I want to add the contents of registers A and B and I give a command add A and B, there can be multiple microoperations uh, being performed at the back end and they can include to transfer the contents of register A to the accumulator, to transfer the contents of register B to the data register, then adding them together and storing the contents of the result to the accumulator and then back to any other register, any desired destination. So an instruction can have one microoperation at minimum and can have multiple microoperations at the back end, while a program is a set of multiple instructions. The instructions of a program along with any needed data are stored in memory, and that's why we determined that memory is a crucial and compulsory part of a computer. So the architecture we are going to discuss in this series of lectures has only one memory, and that memory is shared to store the instructions as well as the temporary data, and it will act as a RAM as well. So the temporary data will be stored inside that memory and some portion of the same memory will be used to store the program or the computer instructions that will tell the computer what to do, and that program will obviously be written by the user. So how an instruction is executed is that the CPU reads the first instruction from the memory at address 0, moves it to the special function register called an instruction register, and then the instruction register has some control circuitry and decoding circuitry hardwired to it, and that instruction is decoded and some respective control signals are generated to control different registers and different modules of that computer. In this particular case, our memory is 4096 cross 16. So this means that each location is a 16-bit wide location and we have 4096 total number of locations. And as we know that the same memory is being shared for the data as well as the instructions, This means that both our instructions and data has the same size. Our data will be 16-bit and our instruction will also be a 16-bit instruction. Now, what are the contents of an instruction? An instruction has information about the operation we want to perform and also an information about the data on which we want to perform that operation on. So the instruction has two parts. One is the opcode or the operation code that gives us information about which operation we want to perform, and the second one has information about the operand. Now operand is actually our data, but we know that in this particular case our data is of 16-bit. So we cannot have a 16-bit data and then still have some free bits or free portion of our instruction to concatenate some information on the operation as well. The opcode must be some bits long and then the data is 16-bit long. But the whole instruction is a 16-bit long instruction. So we cannot have immediate data along with the opcode in a single instruction. So what we do instead in this particular case is that instead of giving information on the exact data, we give the address of the data on which we want to perform that operation. And how long address is required in this case and where the data will be stored? The data is being stored in the same memory. And how many locations that memory has? 4096. And this comes out to be 2 raised to power 12. So this means that we need a 12-bit address to address any given location in that memory where our data is stored. So we have a 12-bit address and we still have 4 bits left in which we can give our information of the operation code. So that's how our instruction is divided into two parts: 4-bit opcode and 12-bit address. Now we have resolved the issue that we cannot have actual data inside the instruction, but we can solve that by giving the address of the data. But what about those instructions that require two operands? For instance, add instruction. Add instruction requires two operands. And as we saw here that we can give address of just one operand here. So if I say, let's say if I write add 20, this means that add the contents of location 20 to what? To the contents of accumulator. So whenever the instruction is involving two operands, one operand is fetched by the address given in the instruction and the second operand will automatically be considered to be placed in the special function register called the accumulator or the uh, processor register. And then the result of this addition will also be saved in the accumulator. So it would be like the data on address 20, data at 20 will be added to the data in accumulator and the result will be placed in accumulator. And this leads us to the term called addressing or addressing techniques. There are many different addressing techniques, including immediate addressing, direct, indirect, register, register indirect, displacement index, stack, etc. But in this particular case, we are going to discuss the three most basic types of addressing, that is immediate addressing, direct addressing, and indirect addressing. Now, immediate addressing means that the operand itself is placed inside the instruction. So in that case, if our data is 16-bit, there should be the instruction should be greater than 16-bit, maybe 5, 6, 7 bits in addition. But if our data is 16-bit and our instruction is 16-bit, we cannot put the data itself in here. And as we said that we are putting address of the data that is smaller than the data itself in this position of the operand. And that is what we call a direct addressing. Direct addressing means that the data is not included in the instruction, rather the address of the data is included in the instruction, while the indirect addressing is sort of use of pointers. So let's discuss each of them one by one. In immediate addressing, operand is the part of instruction. So we have opcode and we have actual operand placed inside the instruction. For example, in this case, add 20 will mean 20 plus accumulator, data of accumulator. And this add will be instructed by the operation code. So add 5 to the contents of accumulator, add 20 to the operand of accumulator, contents of accumulator. That 20 or 5 or any number written there is not the address but the data. So no memory is involved in this kind of addressing. We are not taking any data from the memory, rather we are giving the data inside the instruction. The second addressing technique that we are going to actually use in our basic computer is direct addressing. So the address field or the operand field contains the address of the operand, not the operand itself. And the address is the address of some memory location. So it involves referring to the memory and then fetching the data from the memory and then performing that operation on that data. So direct addressing can be visually explained using this diagram. We have an instruction. There is some portion for the opcode that will give us information of the operation, which operation we want to perform on the data, and the address of that data on which we want to perform that operation points to some address in the memory, and from that address we pick the operand. And then the indirect addressing points to the address of the operand, not it will not provide the address of the operand directly, but it will point to the address where the operand is located, and it is denoted by putting some parentheses around that address. Let's show it to you using this visual representation. So again, we have an opcode that will define which operation is being performed, and then we have an address. Now at this address, the data is not there. This address is pointing to the pointer to the operand. So address is pointing to another address, and then we go to that address and our operand is there. So what is the advantage of using indirect addressing? As we already saw that we can implement pointers using indirect addressing. For instance, if we want to fetch the data from memory location 20 to 2000 and send it to output one by one, what I can do? I can I can write some command that will fetch the data one by one, and then it will keep sending it to the output. So I will say OUT 20, OUT 21, OUT 22, and OUT 2000. So we will have 1800 instructions for that, and our whole memory is has 4000 locations. So we are not going to do anything else in this one. But the same task can be performed using pointers very easily. So let's say we have a variable x and we say x is equal to 20. Now what we do is, and we say OUT x. What is the value of x? 20. So now go to location 20 and fetch the data from that location, not from x but rather from, so this is now location x and x has 20, so now go to location 20 and fetch the operand from there and send it to the output. And let's call this location, this and the instruction of this the location of this instruction to be again agn. I'm going to give a label to the address where this location is placed. Now increment x and then jump to again. What's going to happen here? In this location x was 20, so it will go to x, then from x it will go to 20, take the operand, send it to output, and then increment x. and then jump to again. So now x is 21. So again it will go to x, then it will go to 21, take the operand from there and send it to output and then jump to again. So it will keep on doing this in a loop, and we have only 1, 2, 3, and 4 instructions to perform the same operation that was being performed by 1800 instructions. And that is the beauty of indirect addressing, pointers, and loops. So in this basic computer, we have two addressing modes. One is direct and one is indirect, a single indirect. We can have multiple indirect addressing modes, like we can increase the number of brackets that are presenting in this one, and we can have multiple pointers and nested loops, but we are not going into the details of those because those are related to the programming concepts. For now, we are only sticking with a single level indirect addressing mode. So next up, we have some computer registers. The special function registers that we have in this particular basic computer include the following registers. First, we have processor registers. The first register, and a very important register, is a program counter that counts the program, or that keeps track of which instruction of the program is being executed and which instruction has to be executed next. So a program counter is a counter register that starts from 0 and it keeps incrementing after execution of each instruction. And we know that the same memory is being shared by our program and data. And let me tell you here now that your program always starts from location number 0. So your program counter is by default pointing to the location number 0 at which your instruction 1 is placed. So the first instruction is fetched, decoded, executed, and then your program counter will become 1, and that will point to the second instruction and so on. So your instructions are executed one by one. And as our memory is 4096 words, so the size of program counter, or the size of address to address that memory, is 12 bits. Then the second register of our interest is instruction register. When the program counter points to which instruction we want to fetch, the instruction is fetched and is placed into the instruction register. And in instruction register, we have some decoders and some control circuitry connected and hardwired so that it can generate signals and control the rest of the modules of computer. And as our memory size is 16-bit wide, so our instruction is 16-bit wide and our instruction register should be a 16-bit register. And then we have the address register. Address register also points to the memory, but address register is used to fetch data from the memory, while program counter is used to fetch instructions from the memory, the same memory. So why do we have two different addressing registers to address the same memory? And the answer is that we need to keep track of which instruction we were on previously and which instruction we want to execute next. And the address register keeps on changing whenever a memory reference instruction is executed. So we lose the track. Either we have to first store the contents of address register to a temporary register, then execute a memory reference instruction, and then get the address of our instruction back from that temporary register and then fetch the instruction from there. So again, we need a dedicated additional register to store the address of our next instruction. So why not use a dedicated separate register that keeps counting itself, and that will allow us to keep the address in that register without having to save it once and then retrieve it again. So we are saving some clock cycles here by using dedicated address registers for instruction and data. And then we have data register and accumulator. So one of the two operands is always in the accumulator, while the second operand that is coming from the memory is always placed inside the data register. Why is it so? let me tell you here. So this is your ALU, this is the accumulator, and this is your second operand. Now your second operand is being fetched from the memory, and when it is fetched from the memory, it is placed on the bus. But bus is not a storage. So whenever the next micro operation is executed, the data for the next micro operation has to travel from the bus, the data or address. So bus is continuously being used, it is not storing the data. So we have to store this data on the bus into some other register so that our second operand is safely secured, and that second operand from the memory is stored into the data register, and that is the processor register. So any operand that is coming from the memory is stored into the data register, while the second operand is already there in the accumulator. And finally, we have a temporary register to hold some temporary data. For we can use it for any purpose. And we have some input and output registers. Input register is directly connected to the input lines of the processor, the physical input lines that are communicating, that are taking input from the user, and the output lines are also directly connected to the output, and the output register is also directly connected to the output lines of the processor, that is interacting with the user and sending data to the user. An interesting thing to note here is that both the input and output registers are 8-bit. All the other registers that are dealing with the data itself are of the size of data, but the input and output registers are smaller than the size of the data, in fact half of the size of the data. And the author of this book has very intelligently selected this size to be not equal to the size of data, to give us a concept of some real world scenarios in which we have our input output ports size not equal to the size of data. And using this limitation, we are going to learn what happens when your input output port is smaller than the size of the data and how to handle it. So it will not make any big issues for us. Rather, we are going to learn how to handle this situation. So this is the summary of our computer registers: a program counter and an address register, both of 12 bits, that address this memory, one for the data and one for the instruction. An instruction register of 16 bits that holds the instruction, that's whose size is 16 bit. A temporary register that holds temporary data, it is again, as it is dealing with data, it is 16 bit. Then DR and AC, data register and accumulator, that hold the two operands for the ALU, one from the memory and the second operand by default, and as they are also dealing with data, they are 16 bit. And one input and one output register, both of 8 bits, and a memory of 4096 into 16. So 16 bit locations, so 4096 locations, each location of 16 bit size. And these registers are now connected together, and this memory is now connected together to form a common bus system. And here is the schematic of that common bus system. We have a bus. This is a U-shaped bus. It can be drawn in a linear way as well, so no issues. Here we have S0, S1 and S2, as we discussed earlier, that we have 1, 2, 3, 4, 5, 6, 7, 8 modules that are connected to the bus. So the bus will select the source from where the data is coming to the bus. Then we have this memory unit. So some lines are traveling from the outside of the memory to the bus, and some lines are traveling from the bus to the input of the memory. So memory has a two-way connection with the bus. Then we have the address register. The address register also has two-way connection with the bus, but the thing to note here is that the address register is also hardwired to the address lines of the memory. And then we have program counter. Again, it has two-way connection with the bus, but the program counter is not hardwired to the address lines of the memory. So this means that whenever we want to address an instruction and we want to fetch an instruction from the memory, the data from the address from program counter will be sent to the bus, and from bus it will travel all the way to the address register, and then that address register will actually select that location of the memory from where our instruction is being fetched. Then we have data register. Again, we have two-way connection with the bus. It can both receive and send data from and to the bus. But again, one thing to note here is that the data register is also hardwired to the input of our arithmetic logic unit. And as I said earlier, that this is one of the two processor registers. And the second, and it holds one of the two operands that are required in the ALU operations. The second processor register that is holding the second operand is our accumulator. Again, it has its output connected to the bus, and its output also directly connected to the input of the ALU. So accumulator is also directly connected to the ALU as the second operand. But we can see that the input of accumulator is not directly connected to the bus, but rather it is coming only from the ALU. And that's why we required transfer operation inside that ALU. Because if we want to put one of our operands into the accumulator first, and then we want to perform some two operand operation on that data, we have to fetch the first operand from the memory, put it into the DR, and then that DR is connected to the ALU, and the transfer operation is selected, and that operand is placed into the accumulator. In the next instruction, we will fetch the second operand from the memory, put it into the DR, and then from the DR it is placed in the accumulator along in the ALU at the input of the ALU along with the accumulator, and then any operation is performed inside the ALU and the result is stored in accumulator. So we had transfer operation because of this limitation in our ALU. But now you will remember that we had in fact two transfer operations, not just one transfer operation. We had two transfer operations in the ALU. The transfer operation was repeating. So again here we see that our input register is connected to the ALU, and whenever we give a command to take input from our pins, the data of input register will just travel through the ALU and it will be stored in the accumulator. So one transfer operation is to transfer the data of DR into the AC, and the second transfer operation is there to transfer the data of INPR to the AC through the ALU. And then finally we have IR that has a two-way connection with the bus, TR that has a two-way connection with the bus, and OUTR that can only receive input from the bus but no output, because the output is going to the physical pins to the output world. So this is our common bus system, and this is what we are going to stick to in the rest of our course. So it gives us some opportunities and it defines some of our limitations, and we have to stick to them throughout our course, and we will design our instruction set and all other features of our computer based on this particular common bus system. And this is the linear version of the same common bus system, and I have included that because we have already discussed it. So again, you can see here, memory has a two-way connection with the bus, address register has a two-way connection with the bus, and it is also connected to the address lines of the memory, program counter, data register, and data register is also connected to the ALU. Accumulator has just a one-way connection to the bus, but no input is coming to the accumulator from the bus. The input to the accumulator is coming only from the ALU, and it is also going into the ALU. Again, the input register only to the ALU, instruction register two-way, temporary register two-way, and OUT are just one way. These two figures are effectively the same figures of a common bus system. So I think we now have covered quite a lot about the computer organization and design, and we now have an understanding of how these different modules are interconnected, and what are the limitations and what are the opportunities we have. And we have developed a common bus system, and in the next lectures we are going to further build upon that. So for in today's lecture, our hardware portion is almost complete. Apart from these things, the control of these individual registers and bus and memory and ALU, the rest of the hardware is complete. And now in the next lecture, we are going to move to the instruction set, develop the instruction set, explore it, program it, and then we will come back to designing the control of these individual registers, bus, ALU, memory, etc. So that's it for today's lecture, and see you in the next lecture. Till then, take care, stay safe, goodbye.